Okay, continuing on with PhysioEx 10, Exercise 5, Cardiovascular Dynamics. Activity 6, studying the effect of stroke volume on pump activity. This activity is similar to Activity 5. We're going to have the same setup. We're going to look at a couple of different items that are possible for maintaining cardiac output. So anyhow, venous return and stroke volume. So we'll see a few of the same terms, few maybe new terms, but I don't think any of these terms are going to be that new. Maybe some of the concepts being tied together a little stronger. So anyway, Frank Starling law, we'll look at that as well. I just want to spend a couple of minutes again on the introductory aspect, reminding you once again, stroke volume is the difference between the end diastolic volume and the end systolic volume. So we're going to start with how much blood is going to be in the ventricles once they've filled. That's the end diastolic volume. And then once the heart contracts, we're left with an end systolic volume. So when we subtract the end diastolic volume minus the end systolic volume, that gives us stroke volume. So how much blood is ejected every time the ventricles contract? That's stroke volume. And this is simply how much is in there once it's filled up and how much is in there after it's contracted. Okay, and remember, diastolic having to do with relaxing and filling of the ventricles, systolic having to do with contraction and ejection of blood from the ventricles. So the end volume is what's left over after the contraction. So anyway, a couple of factors that affect stroke volume. So how can we affect the amount of blood that's ejected from the heart? Well, we could alter either one of these, certainly, or both. So we'll talk a little bit about preload, contractility, and afterload. So Frank Starling law, when more blood than the normal volume is returned to the heart by the venous system. So basically, when more blood is coming back to the heart from the body systems or from the lungs, we're going to see a stretching occur in the muscles, the heart muscle, the sarcomeres of the cardiac muscles. So anyway, that was a rough way there. So anyway, cardiac muscles have the sarcomeres. Those are going to get stretched out. If we put more blood, it's kind of like a water balloon. If I have a balloon and I put a little bit of water in it, it stretches. If I put a ton of water in it, it's going to stretch even more. So seems pretty commonsensical, but at the same time, we of course have to give it a special name and make it seem a little bit more confusing than it really is. So all Starling's law states is that when we add a bunch of blood to the heart, we're going to stretch the muscle, and therefore we're going to get a stronger contraction. So more stretching, more forceful contraction. So more blood, more stretching, more forceful contraction. All of those things are the Frank Starling law. So again, pretty straightforward. More blood, more stretching, more contraction, more force of contraction. Okay, so that then generally would lead to then more blood being ejected from the ventricles. So that's what we generally see. So then the stroke volume would go up. And again, that we would see lots of things going up, right? If stroke volume increased, then that means one or both of these increased. And so the end diastolic volume is going to go up or be higher. In other words, how much blood is in the heart just before it contracts. That's the end diastolic volume. So if we increase the amount of blood into the ventricles, we've increased the end diastolic volume, which means we've stretched the ventricles or stretched the cardiac cells. We call that preload. So it gives us a little figure I'll open up. So notice we've got more blood coming in. We've got more stretching of the ventricles. That's called the preload. Okay, so preload results from ventricular filling between contractions, okay, or otherwise known as the how much is the end diastolic volume. All right, so that's a lot of verbiage to just basically say um, that the heart, the ventricles are filling. The more blood we put in, the greater the preload and the more forceful contraction, and the more blood gets ejected. All right. So, ventricular filling could increase when the heart rate is slow. So, if we have a slow heart rate, there's more time for the ventricles to fill. Um, one way. Another way is just pumping, getting more blood sent back to the heart, more venous return. We see that during exercise. So therefore, we're going to see an increase in end diastolic volume and an increase in cardiac output or blood flow. Severe blood loss, so we aren't able to send as much blood to the heart. That's going to decrease preload, decrease end diastolic volume, decrease stroke volume. Dehydration can also do this. So anyway, contractility is next. So that's preload. Then contractility, that's the strength of the cardiac muscle contraction. So how strong is the contraction? And again, we're typically talking about the ventricles here, how much force gets generated from the contraction. We have what are called extrinsic mechanisms that affect the strength of contraction. These are going to be coming from the sympathetic nervous system, neurotransmitters and hormones that can control the force of contraction. So they're getting into like the EKG waves and that extrinsic control of cardiac rhythmicity. So there are also what are called intrinsic controls of contractility. So that's what we're going to be looking at primarily as the intrinsic controls. That simply is sarcomere, actin, myosin connections. So muscle fibers, what's going on with the muscle cells specifically? Those would be the intrinsic factors of contractility. And so again, strengthening or stretching and lengthening. Kind of combined, I guess, is sort of like strengthening. But anyway, ventricles stretch and lengthen. We're really, again, saying the sarcomeres, the muscle fibers or muscle cells. Okay? As the length of the sarcomeres increases, the force of contraction is going to increase. The analogy that's used oftentimes is a rubber band. You stretch and stretch and stretch the rubber band. We're increasing the length of that sarcomere. We let go of the rubber band. The force of contraction is greater than if we just barely pull the rubber band and let go. So that's kind of the analogy that's oftentimes used. We call that a length tension relationship. So we looked at that a little bit with skeletal muscle. Okay. So at rest, cardiac muscles are at less than optimal length to produce a maximum contraction. So when we increase activity, we increase blood flow to the heart, we increase the amount of stretch, we increase the preload. Therefore, we're going to increase the force of contraction. Okay. Okay, so increase in venous return, increase in end diastolic volume, increase in the amount of blood that's ready to be ejected. So again, the heart responds with a more forceful contraction. It's again like the rubber band analogy. We're stretching it out, and then we let go of it, and that's going to cause, in part, the increase in stroke volume. All right, so the afterload then is the back pressure. So when we eject blood out of the ventricles through that aortic or pulmonary, those two semilunar valves, and into, let's stay with the aorta and the left ventricle. When the left ventricle contracts, it passes through that aortic semilunar valve, and the blood travels into the aorta. The semilunar valve closes, and there's some back pressure against that semilunar valve. That's called afterload. So, in order for the ventricles to pump against that aortic valve, for instance, the ventricles have to overcome the amount of pressure, that threshold of pressure that's being pushed against that door. So, in essence, blood, it leaves the left ventricle, goes into the aorta, and the door shuts. The valve closes, but and remember, valves prevent backflow. So, blood is that pushing against that aortic valve in an attempt to go back down into the left ventricle, but the valve is shut. So anyhow, that's creating a pressure. And so the left ventricles, and that's called afterload. And so the left ventricles have to overcome that afterload in order to generate another contraction that's going to eject blood into the aorta. Okay, so this pressure is referred to as an afterload because the load is placed after the contraction of the ventricles. So ventricles contract, and again, those valves, as soon as blood passes through the aortic valve, they're closed up, and we're awaiting the filling of the ventricles again, and then another contraction to occur. So afterload generally isn't something we worry about. I mean, I shouldn't say worry about. It's something that is fairly well controlled in most of us. And now in an unhealthy heart, someone with extremely high blood pressure, hypertension issues, even possibly type 2 diabetics, we may see that afterload in the ventricles. So if an individual has high blood pressure, then the pressure within that aorta and pushing against that aortic valve is maybe going to be say 140 instead of 120, then the ventricles have to overcome or compensate somehow that threshold. So they have to pump harder. So the heart ventricles do end up having to work harder to overcome that increase in pressure. And that again can lead to and if the heart can't do it, then we may see a decrease in stroke volume. So the heart will still pump against it, but we may see that it because it's overworked, so its strength of contraction has decreased. So we do see a decrease in stroke volume. There are several other factors. Again, this figure, I don't know if any of you click on those when you're doing your PhysioExes, but they are generally pretty helpful. All this is trying to show is that if we have an increase in venous return, that means so more blood is going to the heart, or that means a greater end systolic or an end diastolic volume. Okay, the EDV, so more blood going into the heart means we could also label it a higher EDV or end diastolic volume. We would also say that then we're going to have a higher stroke volume. So it just means more blood is there to eject. We could get an sympathetic increase, a stress response to get the heart to increase contractility. Again, more of an extrinsic factor that will increase stroke volume as well. And then lastly, if we have a decrease in afterload, okay, so decrease in pressure, then we'll see an increase in stroke volume. But again, if this pressure, the afterload is high, then we may see a decrease in stroke volume. Hey, say any of these, if we decrease this, so parasympathetic kicks in, contractility goes down, stroke volume goes down. We see a decrease in venous return, therefore a decrease in the volume of blood that gets to the ventricles, therefore a decrease in the amount of blood that we're able to eject. So these are some of the factors that relate to stroke volume. So anyhow, lastly, it reminds us, and once again, what cardiac output is. Cardiac output, heart rate, so how many times is the heartbeat per minute, multiplied by the stroke volume, how much blood is ejected per contraction or per stroke. So cardiac output. Now, generally, we see that around 5,000 milliliters or 5 liters. So, roughly 5 liters per minute is what we're looking for, and what the body attempts to maintain at that homeostatic range. If cardiac output uh, we saw it in the last activity going up, up, up. Generally, the body is going to compensate to not allow that necessarily to happen, and so we'll see some of the factors that play a role. We can increase or decrease multiple different items. So anyhow, when stroke volume decreases, the heart rate must increase to maintain cardiac output. So, again, if we want to maintain that 5,000 milliliters or 5 liter number for cardiac output, if stroke volume goes down, we just looked at what would cause stroke volume to potentially go down. Then, in order to maintain cardiac output, we have to increase the heart rate. So these are inverse stroke volume and heart rate. So when one goes up, the other one has to go down in order to maintain cardiac output. So if stroke volume is high, as we increase the amount of stroke volume, and again, that could be because we have an increase of blood to eject. We have an end diastolic volume that's gone up. We may have a sympathetic nervous system triggering increase in stimuli, triggering an increase in strength of contraction. Starling's law telling us as we increase EDV, we increase the stretch of the sarcomeres, we increase then contractility as well on an intrinsic level. So if that happens, stroke volume then goes up, then what we're going to see in order to maintain cardiac output is the heart rate needs to go down. So anyhow, our pump, as it says in our experiment, and these aren't obviously perfect, but I think they do a pretty good job. So it's the same setup, left beaker. Let's get through these and get going here. You can go through and do those certainly on your own. But we see the same setup as we did in activity 5. We've got the left beaker representing the lungs and the blood in the lungs coming from the pulmonary circuit, heading into the pulmonary veins, over to this mitral or bicuspid valve and into the left ventricle. As blood leaves that left ventricle, we see the aortic valve heading into the aorta, and then the systemic aspect, or the blood to the body. So, a couple of things: 40, 120, and 80 that we are going to leave. And then our maximum stroke. So, we're going to do the auto pump, and it's going to maximally pump 10 times. And the other things we're going to leave constant are these two left and right flow tubes. And again, this represents pulmonary veins, this represents the aorta. We're going to leave both of those at 3.0. So what we're going to be altering is the end diastolic volume or the end systolic volume and the stroke volume. So we're not going to be doing anything with the EDV, the end diastolic volume, the amount of blood in the ventricles that we're able to eject is going to be at 120. So throughout this particular activity, what we're going to be altering is the end systolic volume, how much blood is left over, and then that will tell us then or give us the stroke volume. So let's see. Starting pump volume is set at 120, and we're going to set the stroke volume to 10. So we want this to go to 10. So we need how much blood, the stroke volume is how much blood was ejected. So that would mean our end, if we started with 120 and we ended with 110, we only ejected 10 milliliters of blood. So we're going to say the stroke volume was only 10 for this particular run of the activity. So we're going to auto pump it. We're giving it 10 pumps. And if the stroke volume was set at 10, we gave it 10 pumps, then we would expect to see 100 milliliters were pumped out in those 10 strokes. So we're going to record the data. And remember, we're trying to maintain a flow or a cardiac output of around 5,000. Okay, 5,086.8 happens to be the cardiac output that we're going to maintain through this activity. So, and remember again, cardiac output is going to be stroke volume times beats per minute or heart rate. Okay, so heart rate times stroke volume gives us cardiac output or flow. So if we're going to keep flow as a constant throughout this experiment, and really what we try and do generally is to maintain a cardiac output of 5,000, and we're going to see a stroke volume drop to 10, then that means the only way to get to 5,086 is to get our heart rate bumped up all the way to 508 beats per minute. So impossible, right? That our heart rate doesn't beat that fast. It would never get that fast. Okay. So, thankfully, we rarely do we see a stroke volume of 10. Okay. All right, so pump rate analogous to heart rate. What do you think will happen to the rate when you increase stroke volume? So this is a prediction question. So it's basically saying heart rate and pump rate are the same. We've talked about that ad nauseum. So heart rate, pump rate. Okay. What do you think will happen to the rate when you increase stroke volume? So we want to increase stroke volume. So we would probably see a decrease in heart rate. So pump rate will decrease because we want to maintain cardiac output. So that's what we're gonna guess. So increased stroke volume. So we're gonna, oops, what's going on here? Okay, let us do it. Now it's asking us another question. Let's see. Why did changing the ESV, end systolic volume, so that's what we've been changing, why did that automatically change the stroke volume? Um, well, that I believe what they're going after is this intrinsically altering of the stroke volume to accommodate changes in preload. So, changes in preload. So, again, preload relates to this end diastolic volume of 120. Okay. And in order to accommodate the change in stroke volume, uh, there'd be some intrinsic activity well, that preload has to do with the stretchability. Um, so intrinsically, we have those sarcomeres stretching. So stroke volume is going to go up the further we stretch the heart. Okay, let's see. What are we doing here? Auto pump. Oh yeah, we increase stroke volume, so we should see a decrease in heart rate, which we did because again we want to maintain that blood flow rate. So it's going to have us do this. Repeat this step until you reach a stroke volume of 60. All right, so we're going to keep going. So stroke volume 30, we should see the rate decrease because again, our flow is being maintained or our cardiac output. Okay. Record data again. We continue to see that drop, and that's good. That's what we should see. Okay, now stroke volume is up to 50. We're going to give that 10 pumps, so that should bump this up to 500. And should see around 100 beats per minute or 100 for our heart rate. And then lastly, we've got the 60s. So 60 times 10, this should get up to 600. We can record our data, and we're going to be a little bit less than 100 there. Okay. And I believe, let's see, up refill. Cardiac output is equivalent to blood flow. We know that. Okay, so now what are we doing? Increasing stroke volume by 20. Okay, so the next thing it's going to have us do, increase stroke volume by 20. Okay. Auto pump. Again, 80, 10 pumps. This should get us to 800. Record data. And again, we're staying at that 50, 86 mark, stroke volume of 80. So 5086 divided by 80 gives us 63.6. We're now kind of entering into pretty close to what would be considered normal. Okay, so let's see. Increase contractility. Okay, and then we're going to do it again. 100, so this should put us at 1,000. Stroke volume down here will be 100, so this should be 50.86, 50.9. Okay, and I believe that does it. So we um, click plot the data and you're good to go. And again, you see stroke volume increasing, but maintaining that flow. Okay, so what we end up seeing then is in order to maintain this cardiac output or this flow, we have to alter the strokes per minute or the heart rate. Okay, well, that's it for this activity. The rest you by now, I believe, know what to do. Get to that, and here we go. Describe Frank Starling's law. Remember, increase volume, increase stretchability, increase strength of contraction, increase then the amount of stroke volume. Okay, so that's that. And again, when you're ready to submit, hit print, type your name, click print again, and save as PDF. Okay. That's that. So thank you for watching again, and stay tuned for the last activity in exercise 5.